Hello, my name is Ekaterina Shurkova. I'm a PhD student at the University of Edinburgh. And today I present my work under the supervision of Dr. Dumas on a model of human visual reasoning. Machine learning systems have been successful at many tasks, even sophisticated ones like chess or video games. However, they still fail to match human performance when it comes to switching from one task to another, even with similar games like Breakout and Pawn, or when the goals change within the same task. An example of such a task is a set of synthetic visual reasoning test problems, or SVRT. The SVRT consists of simple A-B categorization problems solved by finding a set of relations that define a category. Here we have an example of two images from one of the SVRT problems. In problem number 1, relation same shape defines category A membership, and relation different shape, the one of category B. And in problem number 4, for example, categories are defined by the relations inside and outside. Humans solve such tasks with a few exposures, they make few errors, and easily switch from one problem to another. However, machines require thousands of examples. The error rates of the machines fluctuate, and they also require training for each class of problems separately. And also, most networks rely on rote memorization and break when that strategy fails. So what we are interested in is modeling a system that can solve SVRT, in part because this task is a microcosm of human visual reasoning. To solve it, a model would need to represent each problem in terms of objects and relevant relations between them, and use those representations to perform reasoning. We also would like our model to be constrained as much as possible by the things we know about psychology. So we would like to create an end-to-end pipeline, but instead of using successful machine learning techniques at each decision point, we want it to be based on successful psychological theories. So the model would start with pixels and move on to reasoning, and it would require us to integrate a set of psychological models at various levels of description, and also to solve a set of unsolved problems. This diagram sketches how we integrate different psychological components. So first comes the early visual processing system and some of its outputs, which we use as simple spatial features. Then we run a simplified version of GIM model for object representation, object recognition. Then the DORA model detects invariants and represents simple spatial relations in a particular format, which is suitable for relational reasoning. Then we have a mathematical model to reduce the dimension space, both when the model chooses which relations to compress, and also when it picks the relevant dimensions for categorization. Next is the compression component, which is a novel mechanism, and it augments DORA with learning complex spatial relations. And then LISA-DORA model is used for reasoning, and in case of SVRT problems, this is categorization. So now let me talk about each component of the model very briefly, but I will be happy to answer any questions afterwards. So the first one is a black boxed version of a simplified early vision. Early vision delivers simple spatial features among many other things. From the images, we extract simple spatial features such as contours of the objects, coordinates of the extreme points, coordinates of the centroid, etc. And then we feed those features into the next module, which is the object representation. The object representation is done as a simplified version of GIM model. GIM is a model of object recognition based on Biedermann's recognition by components theory, where objects are represented as structured arrangements of simple parts of objects. The next part of the model is based on the existing discovery of relation by analogy model, and DORA detects invariants, and it also learns structured relational representations of simple spatial relations, such as bigger than, for example, and it learns them from unstructured inputs like pixel images. So this is the part of the model where it learns by analysis. However, solving SVRT task requires not only simple spatial relations, it also needs more complex relations, such as inside, same shape, and so on. So the model learns complex spatial relations by compressing the simple ones, which I will talk about in a minute. But in order to know what to compress, the model needs to isolate relevant dimensions, so to reduce the space. And we account for this phenomenon with a mathematical model. It uses supervised learning implemented as a type of high sensitivity Bayesian model with rates 1 for dimensions that are relevant and 0 for the irrelevant ones. Basically, at this point, the model is given instances of stimuli that exemplify a particular complex relation, such as inside. And the model compares across those instances and updates the posterior for the presence or absence of a particular relation in the exemplars. So the model keeps the dimensions that are maximally predictive of this complex relation. And then comes the compression component. So this is a novel routine which augments the DORA model with learning by synthesis. We implement it as a compression mechanism for combining simple predicates that the model already learned. The resulting representations are complex, important concepts that people learn and apply. They're not just simply putting the simple concepts together, but concepts like supports, for example, that can be represented as a combination of below and in contact. In addition, compression allows to conserve resources and reduce the complexity of the resulting higher order structures. The model compresses the predicates into representational structures which do not require additional binding resources. The model augmented with the compression routine accounts for data from a study of human category learning in which participants learned categories defined by novel combinations of relations. And lastly, we use analogy making for the categorization process. This is an old school Lisa-Dora mapping algorithm. The model compares sets of structural representations and learns mappings between elements that are in alignment. So this was a brief overview for the components on the pipeline, and now let me walk you through how the model works on visual stimuli. So I'll do that by talking about how it learns the concepts necessarily to solve the SVRT task problems. So first we pre-train the model by giving it experience with a bunch of 2D shapes that it has never seen before and that are different from the shapes used in SVRT images. Here's an example of one such image. Then the model sees the input, it identifies the contours in the image, calls the enclosed contour an object, and represents this object in terms of absolute metric dimensions in pixel space. Then we run DORA, and DORA runs in non-supervised fashion and learns from these representations simple spatial relations. Then for the model to be able to learn more complex concepts, we use a set of labeled instances. So first we expose the model to 40 instances of a labeled concept, for example, inside. And here the label serves just as an invitation to compare. Then we let the model to perform a relevant dimension isolation, and then it runs compression. So from these 40 exemplars, the model ends up with representations of more complex concepts, such as inside, same shape, to the center, on a diagonal, etc. So some of the complex concepts that the model learns are relevant to solving SVRT tasks, and some are irrelevant. And when the time comes to do the SVRT problems, we run the same set of algorithms without the learning on SVRT problems. So when the model sees the first exemplar, it represents it in terms of relations between objects that it has already learned and guesses the category. And with the consecutive exemplars, the model looks at an image, it represents it in terms of relations, and then by performing mapping with the first exemplar, the model tries to identify which relations are predictive of category membership. So let me talk about the results. So in the original study with human participants, there were 20 participants. They solved all 23 problems in one sitting. They were presented with one image at a time. If the participant categorized 7 consecutive images correctly, the problem was counted as solved, and the next problem was presented after that. If the problem is not solved in 35 trials, it was counted as a fail, and the participant moved to another problem. We did the same thing with Dora. So one instance of Dora ran through all of the problems of SVRT task in a sequence, and one Dora run was counted as one participant, and we had 1,000 Dora runs. Okay, so here are the results for all the 23 problems. The very first graph shows an average number of attempts for each problem. So on x-axis problem number, on y-axis is the average number of attempts. And the second graph shows the proportion of fails for each problem. And as you can see, humans were able to solve almost all problems with few fails. And Dora did as well as human on some of the problems and outperformed humans on others. So let me summarize. Firstly, this work shows that the complex relations can be built as compressed collections of simpler, more easily learnable relations. Also, we've got a model which is moving towards an end-to-end computational system that is motivated by successful psychological models. This model outperforms machine learning models in visual tasks, such as SVRT, and also does a much better job matching people behavior on these tasks. In addition, we now have some evidence that some aspects of visual reasoning might be modeled by a system capable of relational reasoning. And finally, this work provides further evidence for efficacy of taking psychology as a very real motivator for a computational reasoning system. We argue that it's fruitful to look into integrating successful computational psychological accounts, perhaps with some combination of machine learning methods as necessary, particularly for the black box stuff, and using psychology-motivated models for more comprehensive theory building. So instead of taking successful machine learning components and having them stand as proxies for psychological theory, what we do is we take successful psychological models and create a fuller account of some cognitive phenomena. So thank you for your time, and I'm ready for your questions.
Thank you, Ekaterina. We have about 6 minutes for questions.
Good.
Oh, hi. Thanks. That's really interesting stuff. I was wondering, have you done some sort of ablation experiments? I'm wondering in particular what happens if you don't have like compression and the dimension identification components. How critical are these new pieces to the whole system?
They are very critical, yes, because the model only knows very simple relations before that. So the relations like above, for example, or bigger, or to the right, to the left. So it's not enough to solve the SVRT task. Yeah.
So just a follow up. I could imagine an analogy model could use multiple relations during the reasoning process itself. It seems like compression might be helpful, but it doesn't seem like it's necessarily required in general, because if you are representing multiple relations in a particular problem, it could be doing the mapping based on the entire pattern. But
Yes,
it sounds
I
like
think,
that's
yeah.
not quite enough here.
Yeah, when you put it that way, I think it might be useful and it might be possible. The problem is with multiple relations, it becomes an overload for the working memory. Yes, definitely you can represent multiple simple relations, right, in one model, but I think, yeah, I think that's what the problem is. The main problem is overwhelming the working memory capacity. Does this answer your question?
Yes, thanks. Sorry.
Thank you.
Okay, one more question. Very interesting stuff. Unfortunately, you didn't have time to show us the actual mechanisms of the model. But if you can elaborate this compression stage, exactly how does it know what to combine, what not to combine? So any kind of more information on the compression stage would be appreciated. Thank you.
So first of all, what it does, it isolates the relevant dimensions, right? Because if we can't just compress everything that there exists in the model's memory. So first we run the isolating relevant dimension component, which what it does, it learns in a semi-supervised fashion the complex concepts. So what we do, we present the model with some complex concepts with the exemplar that exemplify these concepts. And we tell the model that this is, for example, is an exemplar of a relation inside. And then we give multiple objects, multiple stimuli, which exemplify this relation to the model. And it learns the particular combination of simple relations that is needed. So it learns what simple relations predict this complex relation. So then it knows what it needs to compress. And the compression is done by, what's happening is when an object is being bound to multiple roles, what it does, it puts those roles together in a more complex role. So for example, if we have one object that is bound by predicates to two roles, below and in contact, what the model does, it creates a more complex role which is supports, and it actually I have a picture to show you. Yeah, right here. Okay, so here in can you see it? In the picture A, we have three objects: glass, mug, and cup. And glass is taller than the mug, and mug is taller than the cup. So in this case, the mug is bound to two roles at the same time, taller and shorter. And what we're trying to what we are teaching the model is the role in the middle, which is at the same taller than something and shorter than something. So what it does, the model compresses the two roles, shorter and taller, and creates the higher order feature units, which then know what roles they are bound to, so that we can unpack it if needed. So this is what's happening. We are reducing the number of bindings in the model, and it creates a role which is in the middle, so a new type of predicate. I hope this answers your question.
Yes, it gives me a sense. Thank you.
Thank you.
Oh, sorry. Could I ask one more quick thing? If my memory serves me, the SVRT problems have some kind of human rank ordering of difficulty. Some are easier than others. And to what extent does your model capture that? I know it overperforms for some, but basically, does it pick up the differences between the easy and hard problems for humans?
No, it doesn't. At the moment, it doesn't, because the model treats all the relations as the same. And for humans, for example, distance relations is very difficult to pick up. And for right now, our model doesn't have that kind of saliency to relations. But that's our future direction. Thank you.
Okay, thank you.
That's all the time we have for questions. Thank you to all our presenters and our audience, both in person and virtual, and enjoy the rest of the conference.
Thank you.